So now we're going to learn some more techniques for counting more efficiently. And the first technique we're going to learn is complements. Because it turns out sometimes it is easier to count the number of objects that do not have some property rather than the number of objects that do have it. And to motivate why this would be important, let's look at this example that's coming up. We want to determine in example 5 the number of 5-letter words from the letters ERST, such that we can repeat letters, like we could have 4 E's, but we cannot have ERS. Well, I claim the opposite of not having ERS would be having ERS in the word. And I claim it's way easier to find the number of 5-letter words that actually contain ERS than the ones that don't have it. So let's talk about how we could use this and learn from it. So we have to review some set theory. Suppose I have this thing called the universal set. We typically call it U. It means everything. And A is a subset of U. Then we define the complement of A, and we're going to use A bar to be consistent with your textbook. You guys might have used this AC before. I'm totally fine with you using that. In fact, you can use whatever notation you want for the complement, but if it's not A bar and not AC, I want you to define it on your paper so I know you're using the complement. So for example, if you want to do like A with a party hat on top of it, just tell me this is A complement. Or the complement of A on your paper, and I'll totally accept it, no questions asked. But you'll have to define it every time you use it because it's non-standard. Okay, so what is the complement? Well, it's really take the universal set, and it's the opposite of A. So take out everything in A. So if we were going to write it with set notation, it's all the elements that are in the universal set, but that are not in A. And if I want to draw this pictorially, you might have that A is this beautiful set right here. And A complement, let's use like orange or something, is all of this all out here. Okay, so why is this helpful? So I'm just going to remind you guys, review some terminology. So review. This symbol, it means and. It's intersection. And this symbol means union. And perhaps more importantly, let me write it out rigorously with set notation. So I'm just going to say, let A and B be sets. A intersect B equals the set of X and U such that X is in A and X is in B, and it's called intersection. A union B is a set of X and U such that X is in A, or, and this is an inclusive or, X is in B, and this is union. So it's an inclusive or. And the reason that this is important is we're going to use two facts. Basically, we're going to use this fact 1. A intersect its complement. The stuff that's in A and not in A is nothing. You can't be both in A and not in A. Look at our picture. And 2, together, these make up the entire universal set because every element in the universal set is either in A or not in A. So when we put the stuff in A with the stuff not in A, that's everything. So they have trivial intersection, meaning their intersection is the empty set, and they make up everything. Now the last thing we need before we start putting this stuff together is the cardinality of A. So we're going to use bars to denote the cardinality of A. That's the number of elements in A. You might have seen it in previous classes of maybe N of A, but we will use the bars to be consistent with the textbook. Okay, now let's put everything we just reviewed together. And I'm going to say, because of what I just wrote, it turns out right here that the cardinality of U, how many elements are in U, are the number of elements in A union A complement. And that's by fact 2. But we know how to do unions. The number of elements in a union are the number of elements in A plus the number of elements in A complement minus the number of elements in their intersection. And this is a cardinality formula from set theory. And it kind of makes sense because if you guys think about this, I'm going to draw a picture. Suppose I have two sets, A and B. The cardinality of A union B, the stuff that's in A and B, will be all the things that are in A, which are basically this, plus all the things that are in B. But the things that are in B are this. So I've counted the intersection twice, so I need to subtract it out. So it's not the elements that are in the middle, right here, are not counted twice. Okay, so that's where this formula comes from. It's the number of elements in both of my two sets minus their intersection. But I happen to know the elements in the intersection are 0 because the intersection is the empty set. So this is just the number of elements in A plus the number of elements in A complement. Okay, well, what does this mean? So I'm going to say note, since the number of elements in the universal set is the number of elements in A plus the number of elements in A complement, suppose we want to determine the cardinality of a set A. We know the cardinality of A is going to be the number of elements in the universal set minus the number of elements in the complement by just manipulating this equation right here and saying, okay, keep A on the right-hand side and subtract A complement from the left-hand side. Now, when would we have to do this? Well, sometimes it is easier to find the cardinality of A complement than the cardinality of A. And often, even though if we're trying to find the cardinality of A, we need to do the cardinality of U minus A complement. It turns out often the cardinality of U is straightforward to calculate. So it's not bad to calculate that. Now, what would be a circumstance where it would be way easier to calculate the cardinality of A complement than A? So for combinatorics, where this is going to show up is problems that ask you to calculate at least one. In these circumstances, we must either use complements or cases. And I'm kind of glossing over why, but this is going to be something very important to us. When we have at least one, the number of ways to say at least one will be 1, 2, 3, 4, 5, anything more than 1 counts. which makes it very hard to calculate. But the opposite of having at least one of something would be having none of it, which is fairly straightforward to calculate. So now let's try some examples.